Orbitals that have the same n, remember n, l, and m are numbers that are associated with orbitals. So if you have an orbital that have this, if you have orbitals that they have the same n, we say that they belong to the same shell or level. Okay, and we'll see later that orbitals with the same n have more or less the same energy. An electron in an orbital with the same orbitals with the same n would have more or less the same energy, similar energy. Okay, so we say they belong to the same shell or level. Now orbitals with the same n and l are said to belong to the same subshell or sublevel. Okay. Now a more common way of referring to subshells and orbitals is to use a code letter for the quantum number L. So instead of saying L equals 0, we can say S orbital or S subshell. For subshells where L equals 1, we can call those P subshells. For L equals 2, we can call those D subshells. For L equals 3, we can call those F subshells. So that's called the spectroscopic notation. So what would you call the subshell corresponding to n equals 2 and L equals 1? Well, you'd call it 2, and then for L equals 1, you have the code letter is P, so it's a 2P subshell. Okay, so n equals 1, L equals 1 is the same thing as a 2P subshell. For L equals 4, by the way, then L would the code would be G. And those are pretty much most of what we're going to be needing to describe electrons in an atom. Now, an orbital is specified by specifying n, l, and m. In other words, all the orbitals that we use to describe electrons can have associated with them these three quantum numbers n, l, and m. Okay, so if you specify n, l, and m, you are specifying a particular orbital. So for example, if n equals 2, l equals 1, m equals plus 1, you can say that that's a 2p orbital. Okay, L equals 1. Remember the code for this, for L equals 1 is P, right? So 2P, and then you can specify the M sub L down here as plus 1 as a subscript. That's a 2P plus 1 orbital. You can, if you're referring to a 2P orbital, you can, you refer to an orbital as just a 2P orbital. That means you're referring to an orbital that has N equals 2, L equals 1, okay? Now you know that your M can be plus 1, 0, or negative 1. So there are three possible orbitals that you can call 2p. 2p plus 1, 2p 0, okay, and 2p negative 1. So since M goes from negative L to plus L, there are 2L plus 1 orbitals in a subshell. Why is that? Let's see. Let's look at a D subshell. Let's say you have a 3D subshell. Okay, D is code for L equals 2. So, and 3, that means N equals 3. So for this particular subshell, how many orbitals are there? Well, the possible values for L would be negative 2, negative 1, 0, plus 1, and plus 2. So you can have 3D negative 2, 3D negative 1, 3D 0, 3D plus 1, and 3D plus 2. 5 possible orbitals in a D subshell. Anytime you have a D subshell, since your M, I'm sorry, this should be M, your M can go from negative 2 to positive 2. There's 5 possible orbitals you can have in that subshell. See, this is L equals 2, so there's 2 times 2 plus 1, okay? So that gives you 5 possible orbitals. 2 times 2 plus 1 will give you 5 possible orbitals in a D subshell. So in general, the number of orbitals in an S subshell is, well, if L equals 0, remember, for an S, L equals 0. So the only possible value of M is 0. So you only have 1 orbital. So an S subshell is also an S orbital. A p subshell, on the other hand, p is code for L equals 1. So for L equals 1, the possible values of m are +1, 0, and -1. So that's 3 possible orbitals. Okay. About a d subshell, I talked about this earlier. L equals 2 is a code for d is a code for L equals 2. So if L equals 2, your possible m is +2, +1, 0, -1, and -2. There's 5 of those, 5 possibilities. And if you have an F subshell, L equals 3 there, possible values for m would be -3, -2, -1, 0, +1, and +2. That's 7. See the pattern? 1, 3, 5, 7. So if you have a G subshell, you're going to get 9 orbitals. Okay? Now, like I said earlier, if you write an expression like something like 2p, it means you're referring to the 2p subshell or any one of the orbitals in the 2p subshell. If you notice, that a p subshell has 3 orbitals in it. Okay? So how many orbitals belong to the n equals 2 shell? What are they? Well, if n equals 2, okay, let's look at the possibilities. Then L can either be 0 or 1, right? Remember, L can be 0 up to n minus 1. And 2 minus 1 is 1. So L can be 0 or 1. And your M for L equals 0 can only be 0, right? For L equals 1, it can be -1. It can be 0, or it can be +1. So that means you have 1 2s orbital in a 2s subshell. You have 3 2p orbitals. So for a total of 4 orbitals.